Oh, this, okay. Hi, everybody. So my name is Benham. So here's a diagram of what a typical open domain dialog system could look like. So it would consist of multiple different modules, such as an NLU module, a dialog manager, and it can also consist of multiple different responders. And each of these responders can be tailored to work with a specific sort of situation or dialog context. So you can have a responder for movies, music, generic responders for greetings, and you can also have no response generators as well. After each responder returns a response, some sort of ranking strategy would then be used to determine which response to return to the user. And so this work focuses on model-based response selection or response ranking. And for this, we need both appropriate and inappropriate responses in our data to train a model. So I'm going to use appropriate and positive interchangeably and inappropriate and negative interchangeably. And so a lot of current approaches of creating negative responses for training aren't manually verified, and therefore there may be some mismatch during inference time. Additionally, a lot of works only use one positive candidate, but there can be multiple positive candidates for a given dialog context. Quick note, our work focuses on conversations with real users or customers. So due to privacy concerns, all the example dialogues shown in the paper and presentation are from the authors and not from customers. So a lot of prior work in response selection has focused on creating negative candidates for training. And one approach is to randomly select negative candidates from, let's say, random dialogues. So an issue for this is like in the dialogue here on the left, where the user says, hello, a randomly selected response can be completely off topic. And so this could be really easily identified by a response selection model as a bad response. And so we want more stronger candidates to train our model because at every turn, all the responders that we have see the exact same dialogue context. You can also select candidates from within the same dialogue, which can make the candidate a little bit more difficult to learn. So here, the example on the right, where the user is asking about video games, the system response is, what do you find interesting about Roblox? So it's still not as coherent, but the topic is still on video games, so it could still be harder for a model to learn. Works have also tried to generate adversarial negative candidates, such as replacing random tokens in a positive candidate. So here, after the user said that they were playing football today, an adversarial candidate that was generated was, thanks for sharing that story, which is sort of appropriate, but doesn't sound like that great of a response. Finally, you can leverage user feedback. So in the dialog RPT paper, which is a ranking model, up-down votes on Reddit posts were used to train the model. So this figure from the dialog RPT paper shows that certain responses got more upvotes than downvotes. So those would be considered positive responses during training. And then prior work involving positive candidates mostly use only the ground truth positive candidate. So there's only one positive candidate per turn. But like I said, there can be multiple responses that are appropriate for a given dialog context. There has been work in having humans try to write multiple positive candidates. Our work will focus more on positive candidates from models, from response generation models. So the main idea is us curating a data set where we have multiple positive and negative candidates per turn that are manually verified. And we demonstrate significant performance improvement in comparison to using adversarial trained data. And even though this data needs to be collected manually, which can be cost intensive, we still think that the performance gain is worth the trade-off. So our data consists of conversations where real users are interacting with a dialog system through the Alexa Prize framework. And so within the Alexa Prize framework, a user initiates an interaction with some dialog system, decides when to stop the conversation, and then are asked to leave a rating from 1 to 5. So our annotation pipeline is shown here on the right, where we show some conversation context, and then we list all the response candidates that were returned for that turn. And some internal annotators will then label all responses that they deem appropriate. And if none are appropriate, they select some none box that we provide. And this appropriate annotation is based on if the response is relevant, doesn't contradict the dialog context, and also acknowledges the user. And so at the end, all responses that are selected by the annotators are deemed as positive, while the rest are considered negative for our training. So I'm going to briefly go through the dialog system that we use to collect the conversations from users, just briefly going through each module. So the user input is some speech, and then we have some ASR model output the text. And then in our NLU module, we have a set of classifiers that are run on the user utterance to extract things like topic, dialogs, sentiment, entities, and whether or not the user utterance is offensive. And then we have two different types of responders. The first is template-based responders. And as I mentioned previously, there's responders for popular topics that we have, like movies, music, and recent news. And how a template-based responder could be used is that it could leverage what the topic is from the topic classifier to decide which responder to use. And let's say a user mentions a movie name, which we extract from the NER model. We then respond with the information about the actor, the rating, or the plot of this certain movie. And then we have neural response generators. They're all GPT-2 XL models trained on user system interactions collected through the Alexa Prize. So we have a variety of different energy models. The first is just taking in the dialog context as input. The second we call topic energy, which takes in addition to the dialog context, what was the topic of the previous user utterance. And this topic can be like movies, sports, politics, and it's represented as some discrete token and then sent in as input to try to control the system response and try to generate something that's on topic. We also have this knowledge energy where we take in as input some knowledge sentence from Wikipedia to try to incorporate that within the system response. We have this dialog act energy where in addition to the dialog context, we send in some set of dialog acts to try to control how this response is structured. So an example is if we sent in two dialog acts such as acknowledge or ask a question, these are again represented as discrete tokens, and the system response should be able to generate a response that follows each of these dialog acts. And then finally, we have the sentiment energy, which if the user expresses some negative sentiment, we try to control the energy model to try to generate some empathetic response. And so at the end of our collection, which we just call response selection data, or RSD for short, we have around $1,500 for training and $142 for testing. And we have around 17K positive responses and 78K negative responses. And so to compare against the standard approaches in the literature, we follow their approaches where we create like these synthetic negatives. And so we have multiple different training sets, and then we'll train our models on these training sets as our baselines. So going through each one, we have synthetic intra-random, where we randomly select negative candidates from other dialogues. Synthetic intra-random, where we randomly select negative candidates within the same dialogue. Synthetic adversarial, where we place spans in a positive candidate using mask and fill approach. And synthetic retrieval, where we select negative candidates that are semantically similar to a positive candidate. And then finally, to compare against training on one positive versus multiple, we have this data set RSD1 positive, where we just sample one positive candidate per turn. And for all our training variations, we do this sampling 5 times. We train the model, we compute all these metrics, and then we take the average of them. For our experimental setup, we have 2 different types of models. The first is dialog RPT. So this is a ranker that was pre-trained on Reddit data, and we both run it in a 0-shot fashion on our testing data and fine-tune it on our training data. And then we have BERT style models, where we have BERT FP, which is a strong response selection model on the Ubuntu dialog corpus. And so this model was pre-trained on the Ubuntu dialog corpus, and we run it in a zero-shot fashion and also fine-tune it on our training data. And then finally, we just fine-tune BERT base on our training data. So how our BERT model is created is shown here on the right, where we send in some dialog context as input, along with the response being evaluated. And then we take the pooled output representation from BERT, minimize the binary cross-entropy loss to predict whether or not this response is either positive or negative. So for our metrics, we computed mean reciprocal rank and recall at 1 to 5. I'm just going to show the recall at 1 scores because the trend is similar across all the other metrics. So first, if we compare against zero-shot versus fine-tuning on our data, we see if we fine-tune dialog RPT and BERT FP, we get 17% absolute improvement. And this is sort of obvious because we're training on annotated data here. But for this result, if we just fine-tune on just BERT base, this outperforms fine-tuning dialog RPT on our data and BERT FP, which shows that pre-training on the Reddit and Ubuntu dialog corpus didn't actually help us for this task. And this could be because all our dialogs are spoken interactions versus Reddit and Ubuntu, which are more text-based interactions. Training on multiple positive candidates versus 1 leads to a 3% improvement in recall at 1. And then finally, when we compare against training on synthetic data, the best synthetic approaches were synthetic adversarial and synthetic retrieval, but those still achieved a recall at 1 of only 0.53-ish, which still greatly underperforms training on our data, which got a 12.6 absolute improvement. And again, yes, like this can be considered an obvious outcome because we have manual annotation, but still we think that performance gain is worth the trade-off. One of the reasons why the synthetic data creation could not be as good is that these adversarial candidates, the negative responses that are created may not actually match the real world test setting. So a lot of the model responses that you can see is they may have multiple errors, but adversarial candidates that are generated may only have a single error within them. So by multiple errors, what I mean is here the system is asking the user if they would like to learn a fun sports fact. And after the user says yes, the incorrect response in red was, I'm sorry to hear that. So here the system is both ignoring the user requests to talk about sports and also is using empathy incorrectly because empathy was not needed for this turn. Another example is the system asking, have you watched this movie Titanic? And after the user says it hasn't watched it, the system repeats itself about, have you seen the movie? And also is saying, isn't Jack Nicholson in Titanic? So this is both repeating itself and has also generated some factually incorrect response. Now, one advantage of synthetic approaches is being able to create as many examples as possible. So we took 3 of our synthetic approaches and increased the number of negative candidates and then computed the recall at 1. So here on the x-axis is the number of negative candidates that we generate per turn, and the y-axis is the recall at 1 score. And we see that at some certain point, the recall at 1 scores degrade. And my graph is over my text, but basically it can degrade because of the likelihood and the increase of creating false negatives. So an example of some false negatives that can be created is if the system's asking, how's life for you? And the user saying it's not that great. An appropriate response would be like, did something bad happen? And an adversarial candidate that was generated was like, I'm sorry to hear that, did anything happen? So both are appropriate, but the bottom one would have been labeled as negative. So during training, this would have introduced some noise into the model. And another example is if the system's asking, do you like music? And then the system response after that is, what do you listen to in the car? But the adversarial candidate being generated is, what do you listen to? So again, this is the same issue as before. some errors that our response selection model isn't capturing is if there's some incorrect ASR outputs of user utterances, where incorrect ASR outputs could be either word errors or endpoint detection errors. So an example of this is if the system is asking the user, what topic would you like to talk about? And the user says, tell me about. And so here there's some endpoint detection error because we don't see the full user utterance. And the response selection model selected this response. I can talk about movie and plots. And so it just assumed that the topic was movies, but it could have selected a response that sort of would have clarified to the user, like, what exactly are you asking, or can you repeat yourself again? So in conclusion, we curated this data set with manually verified hard negatives and multiple positive candidates. And again, we think that the cost of manual annotation is worth given this large performance gain versus generating adversarial negative candidates. And finally, for future work, we've currently collected a data set to include non-customer data for us to eventually release publicly as well. And yeah, thank you for listening. Happy to take any questions.
Hello. Oh, and thank you for your talk. I was just wondering, when you were showing the graphs of how many negative samples that you used and how that affected performance, why did you not use the same number of negative examples across the board here? On the x-axis, it seems like they're very different.
Yeah, that's a great question. I think like just at a certain point, as it started to degrade, we sort of were like, okay, it's gonna probably not improve afterwards. And for synthetic adversarial, the approach that was used in the paper generated at most to 20 candidates. So we went up to 20, just following the same number that they used in that work.
All right, makes sense. But the synthetic adversarial also falls down at first to 5.
Yeah, I mean, that could
goes up,
just
so
be
maybe
the matter of like, because we're sampling responses, like it really, like how lucky are you at selecting false negatives or true negatives? So it can vary. And so that's the issue with creating these synthetic approaches.
Right, thank you.
Anyone else?
Did you also study the effect of a decoding algorithm on the performance? Maybe a different decoding would have different results.
Oh, that's a good question. No, so all our GPT-2 XL models use nucleus sampling. But for the work that we're doing right now, we're using all our responders are neural responders and have different decoding algorithms. And so we will eventually look into that. Yeah, thank you.
Hi, thanks for the talk. It wasn't, I'm not sure if I missed it, but did you try using the synthetic negative data together with the manual annotations? And did you look at like how much, performance increased with the amount of manual annotations? So could you get by with much less in the way of manual annotations together with the synthetic, do you think? Yeah,
that's a great point. No, we didn't try that. Another thing that we could have done is like decrease the number of annotated data to see like how much does the performance start to drop off. So maybe we need to can collect less data and then collect less data and then maybe combine it with the synthetic approach like you said. So yeah, that's a good point to bring up.
Thanks.
Actually, I have a question. You mentioned at the end the issue with endpoint detection errors. And I think that's a really interesting avenue to go in, especially for dialogue systems, because at that point, the system can say something like a clarification. Tell me about what, right? So do you have future plans on dealing with this? I mean, there's fixing the endpoint problem, but then there's the nice clarifications that can come up because of this. So the model can actually handle those directly as well. What are your thoughts, and do you have some future plans for this?
Yeah, so we did do like some work where we try to create or insert like ASR noise for the purposes of response generation by just sort of having an ASR simulator like add errors and stuff, and then training a response generation model. It didn't have like any endpoint sort of detection aspect to it, but I think we could probably do something similar for response selection, where we like perhaps like add noise into sort of the data that we're training on. That might help.
Any last question? All right, let's thank our speaker.